Nucleosynthesis. Nucleosynthesis is the formation of the nuclei that make up the elements of the known universe. So, what we're going to start with is where do the elements come from that make up all of the minerals, then all of the rocks, all of the other things that we know in our universe. So, in the very beginning of the universe, there's so much energy all in one place that temperatures are beyond imagine. Now, the time where everything is energy doesn't last very long. And I've put a number here on the screen, and it brings up a point that I want to make about using scientific notation. You're going to see that a fair bit during the course. If you look at that decimal number that I wrote with all the zeros, I don't want to do that so often. So if you're not familiar with scientific notation, let me know that so that I can get you up to speed on it. You're going to see scientific notation over and over again throughout this course. So we usually hear that subatomic particles are about as far down the chain as you can go and as simple as you can get. It's really not the case. So all that we know so far is particles called quarks that make up these subatomic particles. Subatomic particles, protons, neutrons, and electrons, but there are particles that make these up, and they have some odd properties that they have these cutesy names pinned on them, but they're mostly really in the mathematics. And don't overly sweat this. We're not going to be dealing with these, with the physics here, beyond just an introduction. And I'm not going to ask you to tell me about the properties of quarks. I just want you to know that they exist and that they make up the subatomic particles. And finally, here are our subatomic particles starting to come into being. So the quarks eventually settle into these three, probably more than that, but three that we're going to deal with, types of subatomic particles: protons, neutrons, and eventually electrons, although electrons may be a type of quark in and of themselves. So we're just now starting to see the particles that are going to make up the universe that we know now. So, right, this is a geology course. So why am I starting with fusion and how stars form elements? Well, elements are what make up the different minerals that we're going to deal with in the course. And so wanted to give you some background of what makes up the things, the atoms, that make up the things, the minerals, that we're going to be dealing with all semester. So, so far, we have just hydrogen, the simplest of atoms. We need to explain at least 90 elements that are heavier than that. And that's where stellar evolution, the evolution of stars, comes in. You get these clumps of gas randomly happen within this mixture at the beginning of the universe, and then those clumps, they have gravitational pull, so they pull in more stuff, more mass, and then they have more gravitational pull, so they pull even more stuff, and that's just a snowball effect, a runaway. And those clumps get bigger and bigger until they press in on themselves so much pressure that they can cause fusion to start. So, to try to make sure you see what I'm trying to say on this slide, the argument on the previous slide was that our sun is not massive enough to just cause the direct fusion of two protons, two hydrogen nuclei, in order to make a helium nucleus. And that's true, it's not. So we have what's called a fusion catalytic cycle. If you've heard of catalysis in chemistry, this is the same idea. It's just at the nuclear level instead of at the overall chemical level. So in this case, we start with some carbon, and we use it with the proton. Now, it's easier to fuse that proton onto the carbon-12 nucleus than it would be to force two protons together by themselves. So the sun is heavy enough, has enough mass to do this. It works through the cycle. It's catalytic because you start with the carbon-12 and you get the carbon-12 back out at the end. But you've taken two of the hydrogen nuclei and fused them in to a single helium nucleus. Another major dimension of radioactivity and nuclear processes that we're going to deal with in this course is going to deal with radioactive decay. We'll use this specifically for dating things, for seeing what happens. It also has to do with the heat that we find in the interior of our planet and why our core is so hot and so active. It might be, it probably is, that radioactivity has a lot to do with where that heat is coming from. So another thing that we're going to do in the course is we're going to use the ideas, the concepts of radioactive decay to determine ages for rocks or minerals or other samples. Now, these two equations that are here, they're going to do most of the work we need, and we can crunch through the algebra and the process of calculating these. I'm going to do an example in a few slides to walk you through it. If you run into any difficulties with doing the algebra with this or anything, let me know, and I can help you out walking through that. But we will need to rearrange these equations as we go. But they'll do the work. These two equations will do the work that we need. Okay, here's that example that I was talking about. Now, you might see a question something like this, and you have to parse what's in it. We know an amount of radioactive carbon-14 to start with, and we know an amount that we have now. And then we further know what the half-life of carbon-14 is. I've rounded it 5,700 years here. It should probably be 5,730, but that's not going to matter. We'll keep the math as is for now. Okay, so this is not going to be the only way you could approach this problem. There are other ways to solve the algebra, as is usual. It's just how I looked at it when I saw the problem and started working it. Okay, so n is how much we have now. That's our dependent variable, so it's the floating value. It could be any point in time. And we don't know what that time point is. That's what we're going to solve for. So that's our t. N sub 0, often I'll just say N naught, that is the starting amount of material. So in this case, N is going to be the 12 grams and N naught is going to be the 32 grams. All right, so I'm going to rearrange my equation. I'm going to take natural log of both sides to get rid of that exponential, and then divide by my negative lambda and solve for t. All right, so then I tend to do it this way, where I solve for my unknown first and then start plugging in values. It's not the only way to do it. I like it because it's a lot cleaner. It's a lot fewer things to write as I'm working through it. Then you plug in the numbers. Make sure you use parentheses in your calculators and stuff, because order is going to matter, whether you divide first or take that log first. You do want to take the log first here. Well, actually, divide the 12 by 32 and then take the log of that. So anyway, make sure you use your parentheses such that you're controlling your order of operations well. And if you calculate this number, you should get 8,180 years. Let me know if that works out. If it doesn't, we can do some other examples. Then here are some what we call parent-daughter pairs. These are just some of the common ones that you see used in geological applications. And in the next few slides, I will walk through some of the ins and outs of them, but there's a lot more that you could read. Remember, this is an intro-level course. You don't need to know all this information. You just need to kind of have a sense of it and be able to go back and look things up when you need to use them. And then one final thing for this introductory slideshow, right? The geologic time scale. This is an extremely simplified version of this, and that's really what I wanted for this course. If you want to get deeper into the time stuff, the Geology 1122 course that follows on after this one really deals with this time scheme and what life is doing throughout it, and how the planet is changing throughout these time scales. And I would strongly recommend it, of course. But then I'm a geologist, so I love that course. But Over here on the far right, you will see MY is millions of years. So if you look at the Triassic and the Permian here, the PT boundary is at 250 million years. That's how you read this thing. Don't try to memorize it, but probably do want to have this somewhere so that you can refer back to it. Like I said, this is a very simplified version. If you want to use a better one, there's a good one from Geological Society of America and stuff. I'll put up some links in the learning management system so you can have some other options. Just be able to look up when I say something about something that happened in the Jurassic or the Triassic or whatever, when that was.